Bonjour à tout le monde. J'ai pas d'anecdote à raconter. Je voulais juste dire que je suis très heureuse d'avoir pu participer, d'être là dans cette conférence qui fête ensemble avec les amis de Denis ses contributions mathématiques et personnelles. Et donc je suis très contente de pouvoir, contente et honorée de pouvoir participer à ça. Bon, je vais parler, j'ai choisi I chose this work to speak about because there will be a little bit of something like Euler schemes, not exactly. So I thought it could be the work which is closest to your interests. Okay, so I will explain you what is conditional propagation of chaos. And this is actually a recent joint work with doing mathematics is also being with friends, and this is an old friend and colleague of mine, Dasha Lukianova, and so we just did this work together. So I start telling you about the particle system that we consider. We have n interacting particles that I call xn, 1 up to xnn. They all take positive values that is important for technical reasons that I will try to explain to you. And they follow something that we call a piecewise deterministic Markov process. So it's a simple evolution. In between successive jumps, we have a drift that depends only on the particle position and on the empirical measure of the total system. And then the capital Z's that are jump processes, so each particle jumps at a jumping rate f, which depends on its position. F is bounded, so there's only a finite number of jumps per finite time interval. And when it is particle I that jumps, then it receives an additional kick that I call psi. We will call that the big jumps. And at the same time, all other particles in the system will also receive a random kick. So this means that I will receive the kicks which are generated by jumps of each particle j, and I call them, well, the general model would be wj to I. Okay, so it's j that gives something to I. So maybe I should say here that initially these kinds of models came from modeling in neuroscience, and then x would be the membrane potential of the RF neuron, and when it is j that spikes, jumps, okay, then it gives some additional input w, which is the synaptic weight of j to I. So this is something that is looking like one of the models that Quentin showed us, okay, except that in your case it was homogeneous, which will also be the case here, okay? So I think I explained everything here. So I already said, so in between successive jumps there is a deterministic flow. And then we have these jumps. So each particle has its own Poisson random measure that is driving the jumps. These Poisson random measures are independent, so that we have independent driving noises. And the jump creates a big jump, which is this psi, and then the small kicks, which will be random actually, which are distributed to all others. Okay? Okay. And for today, I will speak, well, I told you I will speak about conditional propagation of chaos. That means that we consider exchangeable systems, and that means for the rest of the talk, the W's will actually not depend on the pair of particles which are involved. They will be all the same. And that means that all the particles behave in the same way, such that we can describe their joint behavior by the empirical measure. And throughout this talk, mu n will be the empirical measure of the trajectories of all the particles. Okay? And I'm interested in the limit of the mu n's as n tends to infinity. And I just put this slide to tell you the difference between propagation of chaos that you all know very well. We had a couple of talks on that, and conditional one. So propagation of chaos is, well, for suitable scalings of of these kicks that the particles distribute to the others, we will have convergence of mu n, this empirical measure on trajectories, to some limit measure, which will always be called mu bar. Mu bar describes the typical behavior of a particle in an infinite limit population. And if it's deterministic, well, then that means that we are in the framework of propagation of chaos, and that in the limit, any finite number of coexisting particles will be independent. Okay? And in our framework, that works well, for instance, if these W's are something divided by n. Okay? So we studied that in the first work with Anna De Masi, Enrico Presutti, and Antonio Galvez some time ago. Then with Nicolas, I continued on that. Quentin has spent a whole thesis studying such kind of systems, and there are certainly other people who looked on that also. Okay. But that's not what I'm interested in today. So after that, in a couple of papers, that was actually the PhD thesis by Xavier Erny, we considered the case where we have diffusive scaling of the synaptic weights, so where the kicks that the jumping particles give to the others are some centered random variable, where at each jump time we choose a new version of that. So we have IID choices at the different jump times, and the scaling is diffusive, so in square root of n. In this case, in the limit, there will be a Brownian motion popping up because there's a central limit theorem, of course, and this gives rise to common noise in the limit, such that actually the limit of the empirical measures, this measure mu bar, will not be deterministic anymore, but it will be random. And the randomness in mu bar expresses actually the presence of common noise in the limit system. Okay? Good. So there were a couple of papers on this, and then on some point we just asked ourselves, well, what happens if these random kicks are not in the domain of attraction of a Gaussian law, but rather of a stable law? And so, well, this slide is maybe a little bit too much information. So the W's are some stable random variable divided by n to some renormalization factor, xi, and u, we will have independent choices at each jump times. Positive, that's important, is a one-sided stable random variable of index. Well, we wanted to start somewhere, so we started with alpha in between 0 and 1, and then actually we discovered that that is the difficult case. Well, but anyhow, so alpha is in between 0 and 1. Okay, so that means that you have Laplace transforms of your random variables which are of this order. And that is what I'm going to speak about today. Okay. Good. So just to be sure that if you prefer generators, here's the generator. Okay. So I have n particles. Each one has this drift. Each particle jumps independently of the others if we condition on all the particle positions at rate alpha of x position. If it jumps, then it chooses a stable jump height u. So nu is the law of the stable random variable. And the u is added to each of the other particles, renormalized by n to the power xi. And at the same time, the ith particle gets the new position psi of xi. Good. So first question is, what should be the renormalization factor? That's pretty easy. So we use the, how is it called, the stability property. So if you have n independent stable random variables, their sum behaves as a stable random variable if we renormalize by n to the power minus 1 over alpha. And since per time unit, I told you that the jumping weight is bounded. So per time unit, we expect to have capital N, which is the number of particles jumps. So the good renormalization will then be n to the minus 1 over alpha. Okay? Good. I should say that it's important that the u's are really strictly stable, so I will use this stability relation in the sequel. Okay, so we renormalize by 1 to the alpha, and I already said it, so the jumps are simultaneous. So the jumping particle is affected itself and distributes small jumps at the same time to all other particles. Okay? Good. And I will spend the next 10 minutes, or I don't know, it depends on how fast am I, on explaining you what should be the limit process as n tends to infinity associated to the system. Okay? Good, so I rewrite because that's convenient. Well, you see, of course, it's easy to guess the limit here. So the most important thing to understand is what is the limit associated to the jump interactions which are hidden in this process. So the jump interactions, I call them A, well, because it's an additive functional. So ATN, it's the interactions which are basically felt by each particle in the system due to the jumps of the others up to time t. Okay? So I sum over all particles. Each particle is driven by its own Poisson random measure. So we have this acceptance rejection variable z, because we have the position-dependent jumping rate. And the u's, so in u we have the jump heights, which are the stable random variables. Okay? So it's this kind of stochastic integral, and we have to understand what is the limit of that. Okay. So first observation is if the jump weight is constant, then they jump according to a Poisson process. In this case, this sum here is just a renormalized compound Poisson process at weight lambda times n, because I have n particles, and the jump heights are stable. Okay, so this is written here. So if I have a constant jumping weight, then I have 1 over n to the 1 over alpha. Z is the random walk, so there are also random walks in my talk. Is the random walk which has the jump law, which is the stable one, and I observe Z at Pt. P is a Poisson process. Weight n times number. Okay? So question is, what is the behavior of a time-changed random walk? And this is actually a very easy observation, which I wrote down here. So so Z is the random walk which has the increments which are the stable random variables. I observe it after an independent time change, which could be anything. It happens to be Poisson, but it doesn't need to. And then we have the almost sure equality, which is this one, which is just the stability of the stable laws. Okay? So Zp is the same thing as p to the 1 over alpha times something which is a stable random variable and which is independent. And this is actually trivial. You just define this u1 tilde here to be 1 over p to the 1 over alpha this, and you check that it has the same law. Okay? Good. And this independence is, of course, well, that's important for the sequence. Okay. So that means that in the case of constant jump weight in my system, the interaction term of each particle felt due to the jumps of the others, which is this guy here, time-changed random walk. So I will apply this representation. So I have the time change to the power 1 over alpha, and then I just divide by t to the 1 over alpha because I want to have the time dependence. I have the renormalization here, and then you see here I have t to the 1 over alpha, some stable random variable, which is actually in law the same thing as the stable subordinator observed at time t. And I use the law of large numbers. P, I told you, is Poisson at weight capital N, number of particles times their weight. So by the law of large numbers, this converges just to the weight to the power 1 over alpha. Okay? So the limit is what? Is the instantaneous jumping weight lambda to the 1 over alpha times the stable subordinator. Okay? Good. So now F is not constant. And here comes the the pseudo-Euler scheme. So we will cut time into small pieces of length delta and freeze each of these time intervals. So that means that on a time interval in between k delta, k plus 1 delta, according to what I just said, the typical contribution of the interaction term should be the instantaneous jumping weight, so that is the total jump intensity divided by n. It will happen at power 1 over alpha times the increment of the subordinator. Okay? So in the time freezed version, the total intensity is the sum of the intensities, so you have to divide that by n. So you see that that will make appear something like the empirical measure to the power 1 over alpha times subordinator. So if I let the time steps tend to 0 and then n to infinity, we expect that in the limit the interaction term should converge to a stochastic integral of the jumping intensity to the 1 over alpha integrated against the subordinator. Okay? And I guess that is, yeah, that's almost the end of my heuristics. Good. So the limit system should be an exchangeable system, at least if I start with IID or exchangeable initial conditions, where I have an infinite number of particles, which are called bars, to tell you that these are the limit particles, and where the interaction term has been replaced by this stochastic integral. So you see they are all driven by independent Poisson random measures concerning the big jumps. The p bar means that I have thrown away the random jump height u because I don't need that anymore in the limit, because all these jumps u have been merged into this stable subordinator. But you see that the particles are driven by their own Poisson random measures, but they have this common presence of the stable subordinator, which creates a source of common noise. Okay? And this is it's because of that the limit particles will not be independent, but conditionally independent, conditioned on this presence of the common noise, and that gives rise to this conditional propagation of chaos. Okay, and that is written here. So the limit measure mu bar, which will also be the limit measure of the empirical measures of this limit system, okay, will not be deterministic, it is random. And question is, well, if it's random, then it's not just the law of the limit particles, it's something else. And what is this something else? That is written on this slide. So there is the famous, so I have exchangeable particles, so it's something which is almost IID, and you know by the theorem of Hewitt-Savage that it's actually a mixture of IIDs, which is directed by the law of mu bar. What does that mean? That means that I have first to pick a random measure according to its law. I call that Q here. And once I have fixed this realization of mu, then I just take IID copies of the particles. Okay? So if Q is a Dirac mass, that means that I have really IID, and in general, you have some mixture over this. And then if you use a conditional version of the strong law of large numbers, it is easy to convince yourself that then this limit measure has to be the conditional law of each of the particles conditioned on the source of common noise. Okay? And so we get this kind of equation, finally. So we have the drift, we have the big jumps. I didn't write them precisely, so the z bar is this jump process which jumps at weight f whenever x has position f of x. And then we have the interaction term, which becomes this stochastic integral against stable subordinator, and the term which is in front is just the 1 over alpha power of the conditional expectation of the present jumping weight. Okay. Good. So that was the first part of the talk. So in the sequel, I will speak first of all about conditions that ensure us that we have a strong existence of this limit equation, and then I will speak a little bit of the convergence to it by coupling. Good. So, yeah, maybe let's. So you see, well, actually I will suppose that B and psi are, well, we put very strong conditions. So all our coefficients will be bounded, such that we don't have any problems here from the bounded variation part of the, well, everything is bounded variation actually, alpha is in between 0 and 1, okay? But the drift and the big jumps don't cause any problems. Psi and D will be bounded. The problem is here because S has small jumps which are not integrable. We don't have, I mean, we have power alpha or something a little bit less integrability, but not more, okay? And the big jumps are integrable, and that's, the big jumps are not integrable, sorry, I'm saying nonsense, but the small ones are. Okay? So for the big jumps of S, they are in LQ for any Q which is strictly smaller than alpha, and alpha is less than 1. The small jumps are integrable, so I'm in the bounded variation case. And so to deal with this, I need something like a mixture in between L1 and LQ distance. So Q is, for the sequence, something fixed, strictly smaller than alpha. Okay. So, well, a similar problem has been solved by Nicolas some time ago, but in a different context because there weren't these conditional laws. So it actually doesn't work what he does in his paper. But I got inspired by what we did together on the mean field system where we have 1 over n rescaling. So actually what we do here is we introduce a space transform of the particles. So we put them into a bijection. We call that A here. A is a concave function on R plus, which behaves like x to the power q for large x, and which behaves like x for small x. Okay? That's all. So it's a bijection, so if I show that A of x has a unique solution, that is sufficient. So the function will be fixed. You can construct any function you want, and everything I will do in the sequel will depend on this fixed choice of distance function A. Okay? So it behaves like x for small x's, and it's equal to x to the, this equality is important for, to x to the power q for large x. Okay. Good. So here are the assumptions I already cited. So the big jumps and the jumping weight, they are bounded. That means it's psi and f are bounded functions. And they have to be Lipschitz with respect to this A function. Okay? Psi is positive. That means that the big jumps always go up. That is, we're not happy about that, but we are not able to do something more general. Okay, so we really need this positivity. And the drift has to be A Lipschitz as well, both in the space variable and in the measure variable. That means that we consider a sort of A Wasserstein distance on the measures. Okay? And then important, we need to have a minimal jumping activity, actually. That means that F is also lower bounded, not only bounded, to have the uniqueness. So if you want, you can call that ellipticity assumption. Okay. So the limit measure, this mu bar, is the conditional law of the limit process conditioned on S alpha, although S alpha doesn't have moments, at least not higher than Q. For this conditional expectation, actually we have all moments because of these boundedness assumptions. So we can just say that x in absolute value is bounded by something deterministic. This is the drift, and then the jumps occur at most Poisson process. So we have here a Poisson process number of jumps each time I go up, and then I have the influence of the stable subordinator. And so we see that we have as many moments as we impose to the initial condition for the conditional law. Okay? And that is actually convenient. If we don't condition, of course, that's not true anymore. But for mu bar, we will have a lot of moments. Okay. So here is the theorem. So we have pathwise uniqueness for this limit process under these conditions. And we also have, by some Picard iteration arguments, a unique strong solution to that. And I just gave you the proof of the uniqueness result, the sum arguments, which are the most delicate ones, concerning the integral against the subordinator. So I take two solutions of the limit. They are driven by the same noise, so same Poisson random measures, same subordinator, and I consider, so I put them in my space transform, and I consider the distance. Okay, and I will show that that is 0. And let us consider just the stochastic integral against the subordinator. So I write it by means of the jump measure of the subordinator. So we see that the x bar process jumps from a present position to mu to the 1 over alpha times x. And in the tilde process, the same happens. No? And the problem is that the little x, well, of course, we have to cut it into two pieces, into the big jumps and the small ones. So the small ones, I call it IT1, and the big ones is IT2. And you see that the small x, which is the jump height of the subordinator, is multiplied by the current jumping weight. And it's because of this that I need that the f is lower bounded. To have this factor here, the mu factor lower bounded. And the two mu's are, remember, the conditional law of x bar given the subordinator, and this is the conditional law of x tilde, but given the same subordinator. It's important that we have the same source of underlying noise. Okay. So maybe I can go quickly on the small jumps. The small jumps are easy. Basically, for the small jumps, the jump term is a to the position plus something times x minus a of the position. We use Taylor formula. We get out the x. X is integrable if x is small. Okay. So there is no problem. At some point in the calculus, we have to compare the measure of one of the particles minus of the other to the power 1 over alpha. And that is why I need f to be bounded, to have this application here Lipschitz, and it is Lipschitz if I'm on a bounded interval. Okay. Maybe we could work harder, but it's this kind of upper bound that we get. So this is on the difference of the volatilities. If you want, it's upper bounded by that. And then I use that the two random measures are obtained by conditioning on the same noise, such that I get the difference of the jumping weights, and then I use that by assumption all my functions were A Lipschitz, so the difference of the jumping weights are bounded by the difference of my functions. Okay. So this is easy. Well, at least this was an easy part. And for the big jumps, we just compare the after jump positions in the two processes. So the one started from x bar, we add this term, x is big, bigger than 1. And the other one started from x tilde, and we add this term, the same x. Okay. Good. We use a triangular inequality, so actually what I only have to consider is this red term. This is somehow the dangerous one. So I will just tell you how to treat the red term. So we use that A is concave. So I have A of mu minus A of mu tilde, which is shifted by the same position x bar, and by concavity, whatever, I mean, since it's concave, this is upper bounded by just the difference of A of x times the volatility minus A of x times the other volatility. Okay? And then, well, we use that f is lower bounded and x is big. And I impose the condition that A is equal to the power q for large x's. Okay? That helps me to get out x to the power q times the differences of the jumping weights in conditional mean. And the important thing is that we really get out this power q here. Okay, maybe it's too. I stop here. So it's just to tell you that it's important to have f lower bounded to be sure that here we are really on the high x range, and we use the specific form of the distance function. Okay. So all in all other terms are treated in a similar way, and then we get an upper bound like that, and you see that we can use a discrete time Gronval lemma, and that is very much inspired by the work of Karl. Karl, I forgot the year of your paper on. It will be on the last slide, the citation. Okay, so this is inspired by Karl's ideas. And the strong existence is by Picard iteration by using the same function A. Okay, so now I will just spend the last 5 minutes to tell you, once that I have constructed this limit process, how I couple the finite process to the limit process to get the weight of convergence, and this is written here. So if I compare the finite particle system and the limit one, I can actually show that I can construct them on the same probability space in such a way such that their A functions are bounded away by, and then we get a weight of convergence which is not exactly this, because I have to work with a Q norm, and Q is strictly less than alpha. So this weight here is actually only true as Q tends to alpha, okay? But I wrote it this way such that you have some nice weight which is okay. So the proof, I actually already told you the proof. So it will be boring. So as I told you, I freeze time during intervals of time length delta. Delta will depend on n, the number of particles. And then I will just use that in each of these time intervals I have a time-changed random walk, and I will apply the representation that I used in the beginning. So I will produce stable subordinator increments of length delta, which will be all independent, and then I will just concatenate them to get to construct a global subordinator, which I will use to construct the limit process. Okay? And it is here that it's really important to have strictly stable jump heights, because I use this stability property. Okay. So it's written here, but okay. So maybe what I just said is the basic idea, and you're not even, you don't have to read it. So if I'm on a fixed time interval between k and k plus 1, this is the interaction term which is approximated, and that just means that I freeze the jumping weight of my true process to be the one at the beginning of the interval. So it's not a true Euler scheme, of course, because I have the particle system, but I just consider the terms where the jumping weights are frozen. So the total number of jumps is this capital N. Sorry, it was capital P just before. So this is conditionally a Poisson distributed random variable, and the mean is just the total weight of jumping times delta, which is the time length. And well, we will use, as before, a law of large numbers on this total intensity and produce the time change on each of these intervals. Okay, so this is, I have to hurry up. So, yeah, just one, I mean, I already made this comment in other talks of already on the conditional propagation of chaos in diffusive regime. So freezing the time actually allows us to decouple the randomness which is in the acceptance-rejection algorithm according to this position-depending jump, okay, and the randomness of the random jump heights. And that allows me in the limit to get a stable subordinator which is independent of the Poisson random measures, which are projected only on T and Z, these uniform random variables that I use. That's maybe the most important point. Okay? So don't read this. Let me just tell you, so the increment of the interaction term is given on the kth interval by the increment of a stable subordinator. which is sampled at time delta, and it's multiplied by my Poisson random variable divided by n times delta. Okay? So these increments, they are all independent. So as I told you, I will concatenate them to some stable subordinator, and then I will fill in subordinator bridges, but that is not so important. And on the Poisson number of jumps divided by n times delta, I will just use a law of large numbers conditionally on what is happening at time k delta, which tells me that this behaves as the jumping rate at time k delta divided by n, and this is my empirical measure at time k delta. And that's all. Okay. So I skip this. And maybe just some last word. To finally prove the convergence, we use some nice idea, which is we have to introduce an interpolating auxiliary system where I take a mean field version, if you want, of the limit system. Okay? So where I replace the interaction terms by this stochastic integral against the subordinator that I have just constructed by these coupling ideas. Okay. And it is here actually that we will need a control of the difference of the empirical measure of the limit system to the theoretical measure of the limit system conditioned on S alpha. And this is something which is done by using the results by Fournier-Guillaume on the Wasserstein distance between empirical measures and the theoretical ones. If you do that conditionally on S alpha, which works as fine as if it would be unconditional. Okay. And that is all I wanted to tell you. So some open questions. Of course, we would like to tackle the case when the jump heights are not strictly stable, but just in the domain of attraction. Another interesting question would to have a weak convergence rate, not just a strong one, as we did here. Question is also, what would be the typical behavior of the limit system? That's a question for Quentin. Where is he? Maybe I skip this remark, and then of course alpha bigger than 1 should be easier to be treated, and well, we did not start thinking about that. So I stop here. I just wanted to give you some literature. So here's a paper by Karl. So it's from '92. Here's the answer. I wanted to advertise this work by Italian people, which are also interested in Markin-Vlasov limits for particle systems where the jumps are simultaneous, but only with my point processes. And this is the paper with Xavier and Dasha, where we are in the diffusive regime, which is somehow the precursor to this work. Okay.
Thank you. Questions or comments?
Maybe my question is, I think that you are able to find the balance between the size of your step for the Euler scheme and the size of your.
Yeah.
Am I right?
Yeah. Yes, of course, yeah. At some point I have to do that. I don't remember how I chose the delta. But you have to balance all the terms, the errors that you make, and to get the rate of convergence that I gave you. Yeah.
Okay.
So I have a discretization error, actually. I have one that comes from the fact that I approximate the intensity, I mean the time change, which is Poisson divided by n. I use the law of large numbers to replace that. And basically, these are all errors that I make. Now, I have also the error due to the Wasserstein distance, but that is negligible.
Thank you. A question that often arises in neuroscience community when we look at these systems is what kind of computation is performed by the system. Have you given any thought to this question? Does this set of neurons perform any useful thing?
Does it transport information? Well, I don't know. You know that we have proved metastability for these kinds of, I'm not in the alpha stable framework, but we had some metastability results in an easy version of that, which you could interpret as the time an initial stimulus survives in the system. Okay, such kinds of results, we are able to put hands on that. Maybe this is a partial answer to your...
Maybe I have a short and probably stupid question, but in the case alpha equal to 2, you consider a centered random variable, and
yes.
in the stable case, it's a one-sided...
it has to be...
no, answer, but I didn't finish my question. Answer. yeah, go on.
So we really use, I didn't really insist on that, but I have to have positive jumps here.
Okay. So it's a somewhat technical or...
Yes, but because we are not able to, I mean, we use this A function and it's concave only on R plus, so you have to be able to compare positions which are shifted by something positive to what, that it's a technical issue, I'm sure it happened.
You did some simulation to see it's only a technical or a theoretical problem? No, you're not interested in... Okay, so thank you again.